section 5.4, page 5. Today we're going to be looking at the first fundamental theorem of calculus. The first 4 pages of this section of notes was for the second fundamental theorem of calculus, which is actually a tad bit easier to comprehend than the first fundamental theorem of calculus. But we can handle this first fundamental theorem, don't get scared. Alright, so first thing here, I want you to consider some function f of t. So because we've written it as y equals f of t, this is now the t-axis, not the x-axis, and the y-axis here. Here's some weirdo function. I also want you to consider some other function, capital F of x. Now I'm going to pause here a minute, or just kind of go off on a tangent. Excuse me, if you are one of those people who interchanges uppercase and lowercase letters at whim without rhyme or reason, you are going to have trouble with this. It matters. There is a difference between uppercase f and lowercase f. Lowercase f is the height of this curve. Uppercase f is the integral from some a to x of f of t dt. So uppercase f is talking about the area underneath this curve from a to some x. And if we put this up here, kind of to put a visual on it, here's some spot A to some spot X right here. And this A is constant. This X is variable. And again, uppercase F is talking about this area underneath that f of t curve from a to some x. Now that a is fixed, so we'll always start calculating area at that a, right here. But this x moves, so when x is right here, there's a certain amount of area. But a little while later, x might be down here, so there will be some more area. Or x could be way down here, we'll have even more. What I need you to see with this is, regardless of where x is, wherever we put x, there is one answer for that integral, or one answer for the area underneath that curve, which basically is telling us that this capital F is a function. Alright, now I also want you to consider for a small h this function, big F of x plus h. So small h, that distance in there is h, which means this coordinate down here is some x plus h. And if we take that up to the function, we have now added on this piece. Okay, so what we want to do is we want to find the area of this added on section. The area of that added on section can be described by the area from a all the way to x plus h minus the area from a to x. So if we take that off, that leaves us with that added on section. So the area of that added on section would be this function f of x plus h minus big F of x, which you are probably a little bit more familiar in seeing it like this. The area from a to x plus h underneath f of t dt minus the integral from a to x of f of t dt. Okay, now since h is small, h is really small. I had to draw it pretty big here so you could see it, but let's consider what happens if h is small. Then that rectangle is pretty narrow. So we can estimate the area of that added on section. estimate the area of that added on section by using one rectangle. If it's pretty narrow, we can estimate that area by using one rectangle with a left-hand height. All right, so that means then we are going to have this. Big F of x plus h minus big F of x is, oh, it's not equal to anymore, it's approximately equal to, because we're going to get the area, we're estimating the area of that rectangle. And the area of that rectangle, its width is h times its height. Its height is this f function where we plug in an x. We have an inequality here. Let's go ahead and divide both sides by h, and that's legal to take both sides of an inequality and divide by a number. So we have f of x plus h minus big F of x all over h. That's approximately equal to f of x. Some of you are seeing this. You're recognizing this piece. All right, h is small. How small? H is very small, very close to 0. We can't let h equal 0, but we can let h approach 0. And we have the limit as h approaches 0 of big F of x plus h minus big F of x all over h. Well, that's now equal to the limit as h approaches 0 of f of x. On the left-hand side, you should recognize this as big F prime of x. On the right-hand side, when we do a limit as h approaches 0 of f of x, which has no h's in it, it's purely f of x. Okay, I know you don't, this is kind of all theoretical right now, and it's not really clear what this is saying to you. Please tune in to page 6 where we can clean up what this actually means.